Hey, good afternoon, everyone. My name is Kamal Singh Bisht, and I'm Principal Application Engineer at Discal Financial Services. Today, I'll be speaking on autonomous MLOps pipelines, architecting self-healing drift-resistant models at scale. In this session, I want to share how we can go beyond traditional monitoring and build pipelines that are truly autonomous, pipelines capable of detecting problems in real time, adapting on the fly, and even healing themselves within minimal human intervention. So over the next 30 minutes, we'll explore the different types of drift methods to detect them and how autonomous decision engines can make MLOps pipelines more resilient, scalable, and truly production ready. So when we build machine learning systems, we face challenges that are very different from traditional software systems. Let's look at three of the most important ones. First, ML models have dynamic and adaptive behavior. Unlike static code, models learn from data, right, and evolves over time. This means their behavior is not always predictable, and it becomes much harder to monitor compared to traditional applications. Second, we have evolving data patterns. In the real world, data is not stationary. It drifts and shifts. Customer behavior changes, right? Fraud tactics evolve. Environments fluctuate. A model that was once accurate can become stale and unreliable if it is not retrained or adapted. Finally, monitoring ML systems require going beyond infrastructure monitoring. Traditional DevOps tools can tell us if servers are healthy or if response times are fine, but they can't tell us if a model predictions are degrading in quality due to data drift. This requires specialized ML monitoring and observability solutions that can track predictions quality, fairness, and drift over time. So these three factors, adaptive behavior, evolving data, and the need for new forms of monitoring are what make ML systems uniquely challenging compared to traditional softwares. Now let's talk about what we mean by autonomous MLOps. First, we start with self-monitoring. The system continuously tracks model performance, data quality, and overall system health in real time. This ensures we always know when something starts to drift or degrade. Second, we have self-diagnosing. Once an issue is detected, the system doesn't just raise an alert, it identifies the root cause, whether it's a data drift, feature degradation, or concept drift, and it classifies the severity. Third, the self-healing. Instead of waiting for human intervention, the system can automatically fix the issues. This could mean retraining a model, rolling back to stable version, or repairing a broken feature pipeline. And finally, we reach self-optimizing. Here, the system goes a step further. It learns from past actions, adapts, and continuously improves both policies and performance. This makes the pipeline smarter and more efficient over time. So together, these four pillars, monitoring, diagnosing, self-healing, and optimizing, define the vision of fully autonomous MLOps systems. Now let's shift gears and talk about why autonomy in MLOps matters from a business perspective. First, we have reduced mean time to recovery. Short form is MTTR. When system can self-diagnose and self-heal, downtime is minimized, right? Instead of waiting for manual intervention, models and pipelines recover automatically, which saves both time and revenue. Second, improve model performance. Autonomous systems ensure models are continuously monitored, retrained, and optimized. This means more accurate predictions, better customer experiences, and greater trust in AI-driven decisions, right? Third, cost optimization. Manual monitoring, debugging, and retraining can be expensive. Automation reduces human overhead and infrastructure waste while ensuring resources are used efficiently. Finally, risk mitigation. Autonomous MLOps reduces exposure to compliance risk, financial losses, and reputational damage by quickly identifying and addressing issues before they escalate. Um, so in short, autonomy is not just a technical upgrade, it's a direct enabler of faster recovery, higher accuracy, lower cost, and lower risk. One of the biggest challenges in maintaining machine learning system is drift. Let's break down the three main types of drift that impact system performance. So first, data drift. This happens when the statistical properties of input data changes over time. For example, customer demographics, user behaviors, or transaction volumes might shift, right? Even if the model logic is the same, the new data distributions can cause predictions to become less accurate. Second, concept drift. Here, the relationship between inputs and outputs changes. For instance, a fraud detection model, the same transaction features that once indicated safe might now indicate fraudulent because attackers have adapted their tactics. This makes the original model obsolete. Finally, label drift. This occurs when the meaning or distribution of target label changes. For example, if churn in a telecom dataset is redefined or if customer preferences evolve, the model's training labels no longer align with the reality. So together, these drift leads to system degradation. Measuring the model performance declines over time unless we monitor, retrain, and adapt continuously. This is the chart which will show the data drift in action. So this chart shows data drift is shift in customer behavior over time. Initially, transactions happen mostly during office hours, but now they peak in the evenings. If our model don't adapt their accuracy, then business decision will suffer, right? On the left in the blue, if you see, we see the transaction time distribution before drift. Most transactions were happening during regular office hours, between 9 a.m. to 5 p.m. But over time, as shown on the right, in orange, we see a major shift. Now, most transactions are taking place in the evening, between 7 p.m. to 11 p.m. So why is this important? Because models trained on the original data distributions, office hours transaction, that is, may no longer perform well when the behavior shifts to the evening transactions, right? So that means the data drift occurs. This slide illustrates concept drift, which occurs when the relationship between input features and the target outcome changes over time. So on the left, drift, fraudulent transactions typically had much higher amounts than legitimate ones. This made it easy for the model, right, to separate fraud from the normal activity. But here on the right side, fraudsters have adapted, right? They now perform smaller, more carefully transactions that overlap with the legitimate ones. So as a result, the boundary between fraud and non-fraud is blurred, and the model becomes less effective. This highlights a key risk. Even if the data distribution looks similar, the meaning of the data can change. Model trains on old patterns can fail when real behavior evolves. This slide demonstrates label drift, which happens when the distribution of the target variable changes over time. On the left, before drift, the fraud rate is about 10%. Most transactions are labeled as legitimate, and only a small portion is labeled fraud. But on the right, after drift, the fraud rate has jumped to around 40%. That means a much larger shares of transaction is now labeled as fraud. This kind of drift is particularly challenging because the labels themselves, the ground truth the model relies on, are shifting, right? As a result, the model trained on old label distributions may underperform or become biased in the production. So while data drift and concept drift affects the inputs and relationships, label drift directly impacts the outputs and can severely degrade system accuracy if not continuously monitored. Okay, now I'm talking about the cascade effect. So here what happens, suppose we detect drift in the user embedding models. Maybe user behavior has changed and the embedding no longer represent them well. Those degraded embeddings flow into the ranking model, which depends on them to prioritize items. Now the ranking model say produces poor results, even though it was not directly at fault, right? The problem doesn't stop there. The diversity filter, which relies on rankings to ensure varied recommendation, also start failing. The result is actually chain reaction. One model degradation cascades through the system, damaging downstream performance, right? The key takeaway in that in complex ML ecosystem is like issues really stays isolated. A small drift in the one upstream model can ripple across the pipelines, causing widespread quality problems that are hard to trace back to the root cause. Let's go to step by step through the architecture of autonomous MLOps pipeline. So here in the diagram, you can see it all begins with the data sources. These include the production logs and feature stores that constantly generate the raw signals needed to evaluate our models in real time. Without this stream of fresh, authentic production data, we would never know how models are actually performing in the real world. From there, you can see the data flow into the real-time monitoring. This is the first line of defense where the system checks continuously for changes in the data patterns and performance metrics. Think of this as the heartbeat monitor of our pipeline. It tells us whether the model is stable or beginning to drift. If the monitoring layers identifies the anomalies, the process moves into drift detection. Here, the system applies uh, tests to confirm whether there is a genuine distribution drift or whether performance degradation is occurring. This is where we differentiate between normal variability and real drift problem that requires action. So when drift is confirmed, the alert system comes into play. So here alert systems come to play. The alerts are not just alarms, they are classified based on severity. So for example, minor deviation might simply be logged, while critical performance failures immediately escalate. This ensures that attentions, whether human or automated, is directed where it's needed most. So now at the center of this entire pipeline is the autonomous decision engine. This is really the brain of the system. It doesn't just collect signals, it interprets them, applying policy-based automation and performing a risk assessment. It decides whether to retrain, or to roll back, to deploy incrementally, or in some cases to pause altogether. Once the decision engine takes over, the pipeline becomes self-healing. For example, if drift is caused by evolving data, the system can automatically trigger retraining of fresh data and fine-tune the model parameters to restore accuracy. If retraining doesn't make sense, or if the new version is unstable, the system may roll back safely to previous model version that is already proven reliable, right? Sometimes the issue isn't the model, but the feature themselves, right? What are the inputs you are putting into that your model? In those cases, the system can perform feature repair by automatically reselecting or adjusting features to fix broken pipelines or corrupted data flows. Another option is canary deployment, where a new or retrained model is rolled out gradually to a small portion of traffic, right? Uh, if the canary, during this stage, A/B testing helps validate performance before full rollout. If the canary fails, it's withdrawn without causing widespread damage, right? And in the most extreme scenarios, say in critical industries like healthcare or finance, the circuit breaker mechanism kick in. That forces the system into fail-safe mode, ensuring no harm is caused, and it can even require human override when the stakes are too high for automation alone. So all of these self-healing actions are coordinated with the model registry. This is the central source of truth where every model versions and all metadata are recorded. It guarantees versions, control, auditability, and traceability, key requirements for compliance and long-term governance. From there, successful models are deployed into the production. This stage is about reliability at scale, automatically handling load balancing and auto scaling to ensure the system can meet demand under real world condition without interruption. Finally, the condition feedback loop closes the cycle. Performance results from deployment flow back into the monitoring and even in the future stored themselves. This means the system not only reacts but also learns and adjusting future policies and improving over time. So taken together, this entire architecture is designed to make MLOps pipelines autonomous and resilient. It reduces the amount of firefighting required from engineers, right? Prevents long downtimes and ensure that models adapt to real world challenges quickly and safely. So what we end up with is not just automated machine learning, but self-healing machine learning, an ecosystem that can monitor, diagnose, and recover almost entirely on its own. So let me break down some of the components from this architecture diagram. So first, the data sources. When we talk about autonomous pipeline, everything begins with the data sources, right? The foundation of the entire system. So the first key source is production logs, which captures real world activity. Requests sent to the models or inputs or outputs, performance metrics like latency, and even business outcomes such as clicks or conversions can be sent to as a from the data sources, right? These connections help us understand not just what the model predicts, but how well it performs in driving real value. The second is the feature stores, the structure memory of the ML system. It maintains consistent feature definitions, store baselines for drift detection, tracks data quality and lineage, and preserves training snapshots for reproducibility and rollback. Together, production logs and feature logs form the feedback backbone of the pipeline, enabling continuous monitoring, drift detection, and autonomous recovery. So here, the next is real-time monitoring is the core of an autonomous MLOps pipeline. It ensures we continuously observe the model behavior and the system performance after deployment. It starts with performance tracking, measures metrics such as accuracy, precision, recall, or latency to confirm the model is performing as expected. Next is prediction distribution monitoring, which detects unusual or skewed outputs before they impact results, right? We also monitor input data quality, ensuring data is complete, consistent, reliable, since poor data directly affects model performance. System health monitoring keeps track of infrastructure such as API responsiveness, resource usage, and potential bottlenecks. Finally, feature distribution monitoring helps detect data drift, signaling when real world patterns start to change and retraining may be needed. So together, these all layers create a 360-degree view of model data and system health, keeping the piping stable and trustworthy in real time. Now I'm going to talk about how we can detect different types of drift. So now let's look at how we can detect data drift, right? One of the key challenges in maintaining reliable machine learning systems. There are several methods each focusing on different aspects of the data. First, we have statistical tests such as KS test or PSI test or chi-square test. These are primarily used for feature level drift detections. They help us identify whether the distribution of a particular feature has changed significantly between training and production data. Next, the model-based approach. Here we train a secondary model to differentiate between old and new data. If this model performs well, it indicates that the underlying data distributions have shifted, a sign of multivariate drift, right? Which captures interactions among features rather than individual ones. Then performance tracking, one of the most practical ways to catch drift in production by monitoring metrics such as accuracy, precision, or recall over time, we can detect concept drift, meaning that the relationship between inputs and outputs has changed. The next is, before that, the other method is visualization. So where we can use a visualization tools such as dashboard, drift detection libraries, or observability platforms to get quick insight and visualize how data characteristics evolve over time. The next is concept drift. This slide explains how we detect concept drift. which occurs when the relationship between input data and the target output changes over time. We start with performance tracking, a drop in accuracy or other signals that the model is no longer aligned with reality. Next, statistical tests on prediction errors help detect changes in the target distribution, showing that models' assumptions may have shifted. For streaming or online system, algorithms like DDM or Adwin continuously monitor error rates and detect real-time drift automatically. Retrain comparison methods then validate drift by comparing old and newly trained models. If their behavior differs, a concept drift shift has occurred, right? Finally, tracking feature importance. Drift offers an early warnings showing that which inputs are becoming less relevant before major degradations happens. Together, these methods gives a layered approach to detect and respond to a concept drift, keeping models adaptive and accurate over time. Uh, the last third one is label drift, which occurs when the distribution of target label changes over time, even though the input features remain consistent. Such drift can lead to a degrade model accuracy and misaligned predictions if not detected early. To identify this, we begin with statistical tests like the chi-square or KS test, which reveal changes in label distributions between the training and production phases. And next, the PSI helps measure the magnitude of drift, providing a quantitative view of how much the label distribution has shifted. We also use the metric monitoring to observe the impact of drift on performance, tracking changes in accuracy, precision, or recall to detect deviations that indicate imbalance or changing patterns. Right. Finally, automated tools combine these techniques to deliver a comprehensive drift report, pinpointing when drift occurs and how it affects the model. So by integrating statistical analysis, PSI measurements, and automated monitoring, we can maintain model stability and ensure early detection of label drift and trigger timely retraining or recalibration. So this slide illustrates the automation decision engine, what I discussed in previous slides. The process begins with inputs from three sources. Drift alerts highlight the type and severity of the drift and provide metrics and scores. Context data supplies situational awareness. And such as traffic levels, time, and schedule. Model metadata, including version histories and past performance, helps the engine understand the behavior of previous runs. So these are three different types of data. Once the inputs are collected, they flow into the decision pipeline. The first step is situational analysis, where the system determines what is happening, why it is happening, and how severe the situation is. From there, policy matching takes place. The system compares the scenario with the predefined rules and policies, identify priorities, and suggest potential actions. This leads into the risk assessment, where both business and technical impacts are measured. Timing is considered and cascading risks are analyzed. Finally, the engine moves into the action selection, choosing the most suitable fix, adjusting fix if the risk is too high, and preparing an execution plan. Before any action is taken, strict safety checks are enforced. These checks include circuit breaker or rate limiting, dependency validations, blackout windows, rollout provisions, and human overrides. If the checks are successful, the plan moves forward into execution. If not, the process is escalated to human operator for review. When the engine is cleared to proceed from here, it has a wide range of actions available. It can initiate an automatic retraining process with fresh data and hyper parameter tuning, or roll back to stable versions if needed, or repair features that have drifted, or deploy changes gradually using canary testing. In more serious cases, it can activate a circuit breaker to enter a fail-safe mode, schedule changes of peak hours, or escalate the issues with complete context and recommendation to the human. So execution itself is carefully managed with pre-flight check, progress monitoring, and error handling. So after actions are taken, the system validates results um, by asking whether the problem was truly resolved or not, whether new issues were introduced, and whether performance improved or not. So even every cycle feeds into the learning module here, uh, where success rates are tracked, risk models are refined, and policies are continuously updated. So this ensures the system becomes smarter over time. Decisions are guided by the severity of the issues, risk assessment scores, historical success rate, and the current state of the system. So over time, the intelligence of the system can scale. It starts with the basic rule-based decisions, grows into policy-aware responses, advances to self-learning, and ultimately evolves into prediction decision-making. The benefits are substantial: continuous autonomous operation around the clock, response time measured in seconds rather than hours, the ability to learn from past experiences, and the reduction of the repetitive human effort. Um, as we look ahead, the future of drift detection and monitoring opens up several exciting directions. First, the explainable drift detection will be crucial. So models must not only detect drift, but also explain why it is happening, right? Making decisions more transparent. And next, the multimodal drift monitoring will handle diverse data types like text, images, and logs together, essential for complex AI and observability systems. Benchmarking and standardization will ensure consistency across drift detection methods, enabling fair comparisons and reliable baselines. We will also see human-in-loop drift approaches where experts collaborate with AI to validate or correct model behavior dynamically. Another key area is IR in generative AI and LLMs. As LLMs evolves, drift in prompt response behavior needs to track and mitigate it. Finally, casual and counterfactual approaches will move us from correlation-based drift to understanding true causal relationship. So enhancing root cause analysis and model reliability. So this is the future direction. Um, as we wrap up, I want to leave you with three key takeaways. First, drift is inevitable in machine learning systems. It's not a question of if it happens, but when. Building proactive detection and mitigation pipeline is the only way to ensure long-term reliability, right? Second is like autonomous decision engines and self-healing MLOps pipelines are no longer futuristic ideas. With the right monitoring, safety checks, and retraining strategies, we can make systems that adapt on their own, reducing downtime and human toil. Finally, this is just the beginning. From explainable drift detection to multimodal monitoring and human-in-the-loop design, the future will bring even more robust and intelligent approaches to keeping AI trustworthy and effective. So thank you for your time and listen today. I would be happy to take questions or discuss how these ideas might happen to your own systems.
First is, do you have an example that you can share with us with with a pipeline with the architecture you present? So maybe, Kamal, I don't know if you have shared that example on open source on GitHub, but folks maybe can reach out to you offline and get an example of that pipeline itself, like which manifests the architecture you showed. That will be helpful for folks.
Yep, sure. So I have my LinkedIn address there. You can connect with me, and I can explain you. I give more examples about that. Yeah.
Perfect. Thank you. So guys, feel free to reach out to Kamal on LinkedIn. Sangeeta is asking, how do you determine the trust in autonomous decision engine to carry on the right action?
So there are a couple of things, right? I mentioned the architectural diagram, right? So where there are different algorithms and other things are stuff there, which will identify if you are trying to change. For example, you are retraining, right? So you are retaining the model again. So how you you will find out, okay, after retaining your model is perfect or not, right? So there are different metrics are based on that. You can decide that, okay, I retrained the model, now this trained model is good or not, and based on that you can decide to carry on with that right actions. And also after that, there's also like block where decision engine is there, right? There are a couple of components are there which can figure out, okay, this is the right direction or this is the right action we have to take. So there are multiple things. For example, one is like you have retrain, or you have to see that, okay, the features are proper, so you have to adjust the features. Those type of things you have to do. That decision making engine, right? It will find out. So different algorithm inbuilt in that, and that will figure out what action should be taken.
Okay, thank you, Kamal. There's one interesting question. I'm going to get to the end of the queue, actually. Curious to know if this architecture has been implemented in reality and what tools does it rely on?
Yeah, so this is like a research base, or I would say that still in the progress. So yeah, definitely. But I would say that a couple of things already in place or implemented, but not the whole things. But yeah, again, yeah. So, but couple of things are then not implemented from this architecture, but most of the things are working.